Okay, so this is a great event, mostly because the people that I asked to speak are amazing people. They'll give you some amazing talks about directions in the theory of computer science. And I asked them to present it both what's the most important result in this field, as well as what are the open directions. So students who are here could take it as a cue, invitation to work on these problems and try to solve them. So now, Gil, you want to start?
So thanks all for coming. And our first speaker is Leslie Valiant. Please.
Well, thank you very much for inviting me, and thanks very much for for coming this morning. So the topic I'll talk about is something very close to my heart, and it's been very close to my heart for a long time, and partly because there's a lot still to do, a lot unresolved, so I think it may be an appropriate topic. So basically it's about machine learning and how many of us think it's a great thing, but it's not everything. And so that's the general motivation. And so there are also many approaches towards machine learning, which various people have taken in. And so I'd like to emphasize that mine came through cognition, so that's what intrigued me, and that's what I wanted to understand, and that's how I got to machine learning, and that probably shows through. So the basic background was that cognition is a spectacular phenomenon, amazing. So there must be some theory behind it. It can't be just some engineering kludge. It must be something which theoreticians would enjoy. It's some large-scale phenomenon. So that's what brought me there. And kind of the most basic question about cognition as a theoretician is what's the correspondence between what's inside your head and what's outside in the real world? There must be some amazing correspondence. What's the correspondence? And you call that a semantics. So if this machine inside your head works and performs so well in the real world, there's some really neat correspondence. And so what this correspondence is, so certainly those of us who've worked in machine learning, so many of us believe that its correspondence is statistical. So that's how you should express the semantics of what the representation is in your head and the real world. And so this wasn't always so. So when I started in the early 80s, almost no one was saying that cognition is a statistical phenomenon. It just was what people thought. People thought maybe of logic, but not of statistics. Okay, so my kind of favorite historical comment, which I like using also because I think the problem I'm attacking is a very ancient one, is from Aristotle, who said that all belief comes from syllogism or induction. So if you have a belief about something, about what the weather is going to be like tomorrow, he said there are two ways you could have arrived at your belief, and one is through syllogism, which is what we call logic now. Okay, that's become mathematical logic. That's what syllogism became. And so induction is generalization. He didn't discuss that very much, but that problem became the philosophical problem of induction, which went down the centuries, kind of petered out a little bit. But so now it's really been taken over by learning theory. So learning theory explains how it's possible that we've seen different examples of chairs, and amazingly, although the examples we've seen are different. When we arrive and we haven't met before, we generally agree on where the chair is. It's an amazing phenomenon. Philosophers couldn't figure it out. But now it's so well solved that you can't even interest anybody in it because machines can do it so well. So if you try to explain to people now this amazing philosophical problem, how is it that you can generalize? People don't even see the problem because machines can do it. Okay, but still there are these two big approaches, which is mathematical logic and learning theory, which is statistics, and there's always kind of competition between them, and so Aristotle's question still remains. What is the basis of he says syllogism and deduction. Now I want a common theory of the relationship between what's in your head and what's the world. So there are two options here, and so the question is which one is right. And so what's interesting, what I like pointing out is that so when I first started talking about using this Aristotle quotation, why I was using it is to show people that, look, Aristotle was a smart person, and even he thought that induction had some meaning. But obviously logic has. Okay? But in the present day, when there's so much enthusiasm about machine learning, I mean, I'm using this in the opposite direction. Everyone thinks that induction is everything, and logic is nothing. Okay? So basically what this talk about is, the position I'll take is that we have to take some intermediate position and balance the two to get further in AI, and the question is how to do it. So in fact Aristotle didn't do a very good job, because in the book this quotation is taken from, 95% is all about logic. Maybe 99% is logic. Okay, so I think he doesn't approach it that very much. Okay, so so that's the philosophical background. Okay, so what should we do today? So what I'm interested in is for the two. And of course, statistics is very different from the traditional logical semantics, like Tosky semantics. So we need a common semantics. So what I'll do isn't mystical. I don't find the third semantics. What I'll do is I'll try to force logic into the semantics of learning. So so if you try to redefine logic, standard logic, in terms of this probabilistic machine learning semantics, what you get, what you need to get, what's missing. Okay, so that's a philosophical one, but there's a practical motivation which maybe is a reflection of that. So the question is, so what's the main problem of artificial intelligence? Well, in Turing's view, it was the problem of what we call common sense knowledge. How do you put into a computer data which is kind of inconsistent, hard to write down, and things like that? And so the view here is that we will do it using this approach. So we'll put knowledge into a computer, and we'll have the computer learn. So the learning will give it robustness. If there are inconsistencies, the computer will learn itself out of it. And the only way of getting all this knowledge consistently in the machine is if it does learning. Statistics gives you robustness. But then once you've done that, you also want the machine to be able to reason on this. Okay. So the question is, on this probabilistically learned knowledge, what can you do as far as reasoning? So this is, and then so I'll talk a bit about the theory, and I'll also talk a bit about potential tests of this using real data. Okay, so did Aristotle own a cell phone? No. Okay, very good. Yeah. Okay. Okay. So so the question here is, again, we're trying to look at these two approaches. So one approach is a total belief in machine learning, idea that if you're given all the data, say, from the internet, and you train your machine on all the data on the internet, would you be able to answer this question using standard NLP and machine learning? Does a single black box inductive learning solve all the problems of the world? And of course, we can't resolve this question by just having single examples, but this is supposed to suggest to you that, so in this case, we can all answer the question, but it seems that we use some reasoning. It's not that if you went to the internet, there'd be thousands of sentences about what property Aristotle owned, for example. Okay, you couldn't find this list of what he bought it. So we use a little chain of reasoning. Okay. So let's do this a bit more systematically. So if you want to do AI, we want to pursue this example, but how do you do it more quantitatively? So a favorite test problem of mine is word completion. So I give you a sentence, and this is best done like on a newspaper headline or a website news headline, which are usually fairly concise. And I delete a word. You have to guess what the word is. And why this is of interest is it's a bit like the Turing Test, that it uses general knowledge. You don't know where you need to. Okay, so so you have to take it from some website. So I happen to take it from some English language Vietnam news website recently. And so I give you an example. So it's a sentence with a word missing. Margaret surviving as Classico leaves delicate. So is this nonsense, or is this obvious to someone? Yeah. Sorry. Okay, that's possible. Okay. Any other experts on Spanish football? No. Okay. So this happens to be about Spanish football, and okay, it's La Liga. Okay, so blank faces here. But so my point is that this was an easy problem. Okay. Because if you look at the web, there's 77 million hits if you look for sentences with Barca, Classico, and La Liga. Okay, so Barca. Okay, okay. So it stands for Barcelona for the experts. Okay, good. And even more so, so if you just look at as Barca and Classico, you get only twice as many hits. So it sounds as if, okay, so Barca is a team, Classico is a certain game between that and another team, and La Liga is the Spanish league. And it looks as if, in half the sentences with Barca and Classico and the missing word, there's La Liga in it. Okay, so it looks like something very promising for some NLP machine learning box. Whereas if you had to guess if the Classico was missing, it would be a bit harder. Okay. So this is just a hint that a machine learning box applied to these billions of sentences on the web should do pretty well on this. If even these are such very frequently co-occurring words, you can figure out that you're talking about this Spanish football league and whatever. Okay. So anyway, so this was easy. A lot of data. And just from the linguistic constructions, you probably didn't have to understand what this thing was about. Okay. Anyway, so this one was easy. And another one, again, this is from this Vietnam website. 20 agreements during visits as an envoy. Sorry. Okay, that's very, very close, extremely close, but Obama, very good. Yes, Obama. Okay. Okay. So again, the one thing this illustrates is that intelligent performance is placed somewhere. So you need some specialist knowledge of where the source of information comes from. The fact that Vietnamese are interested in Spanish football is something else. But okay, so again, this one was a harder one because if you look at the agreements in Obama and visit, there's so many okay, so a far smaller fraction of sentences which have agreements and visit have Obama in it. So probably people who got Obama knew that Obama had visited Vietnam, and it was a plausible thing. Okay, so you use some previous knowledge. Okay, so in fact, the times when you have to use reasoning, the most obvious times is when there's some new news, for example. There's some new data, and it's not some universal. Yeah, that's the day. Okay, very good. There's some old. This is some old reference. It was on the website, but it's some older date. Yes, yes, misleading. Sorry.
So count is the correct answer.
Well, except maybe there weren't 20 agreements. So no, I don't know. Okay, yeah. Okay. But the okay. So the main feature of this word completion problem is that there's a ground truth. Okay, so whatever the website says is the truth. You can't complain. Okay, okay. No. I'm doing very. Well, what I'm suggesting is that if you had a proper NLP system with backed up by a machine learning box, you could do far better than this kind of analysis. But if there were just no examples of sentences with those triples, then you probably wouldn't have much data to learn from. Okay, so the fact that once there are millions, you could start discussing. I could have given you examples where there are only six things on the web which have that sort of words. In which case, certainly you'd have to use some sort of reasoning. And also, you can find some very easy ones where you know the answer. Okay, so okay, so I'll come back to this because this is a test. Which, whatever theory you have to answer my problem, you can try to test it on this data. Okay, so this is a real, you can do a rigorous test on this. Okay, and I do want to claim this is close to the Turing test. So the main thing about the Turing test, so the second point is that, he didn't say thinking intelligence is to do with playing chess. He said it's to do with unrestricted knowledge, the Turing test. And he also wanted to measure something. You have to count how many times you're right compared to how many times you're wrong. It's not informal philosophy. You measure performance on unrestricted data, and this word completion test is a good one, I think, because there's ground truth and lots of data. I suppose what one emphasizes with learning theory is that in any kind of learning, the examples come from some distribution. Maybe from the Vietnamese news website, it may be from somewhere else, but it comes from somewhere, and you are expected to perform well, at least in the same world, and not somewhere else. So we have to be, we can't expect performance which is good in every world. Turing may have been assuming a more uniform world, and second thing is that we do insist that everything we suggest as far as computation has feasible computation and also feasible error control in the sense of learning theory, that you tolerate errors, but you can drive them down under some control, as I'll explain. Okay, so the approach I've been pursuing to the problem, to the theoretical problem, I call robust logic, which I'll describe, and also potentially this you can test for the word completion problem, and I'll give you some naive experiments on that. And okay, so so now I'll describe what robust logic is. So what do you have to do to be able to look at these sentences and do better than the standard black box machine learning thing, doing the best NLP? Okay, and the basic answer will be that in this robust logic, the knowledge you'll carry around isn't a single black box. It'll be thousands of black boxes. And the thousands of black boxes are like different rules. You've learned different facts about the world by one rule, one box for each fact. And then when you reason, you have to, a bit like in reasoning, you have to kind of have a bit of architecture and some rules of inference of how you combine these. So you don't lose learning at all. You retain all these advantages of machine learning, but you try to build on top of it. Okay, so the basic idea, which for computational complexity reasons one needs, is a mind's eye, and which is like working memory in cognitive science. And here's the idea that you wake up in the morning, you open your eyes, and you think. And you can imagine a number of objects, okay? Because psychologists talk about a number of objects. You can keep your short-term memory is small, so some number, let's say 20. And then you start thinking, and what are your thoughts? Maybe, so your thought is you think of your dog, your first thing you think about, and then you want to please your dog. And so these, to a token, you can assign some relations, some predicates. So one token, you say, this is my dog. You think about it. And then, what does my dog like? So you have this relation thing, which you can apply to things. And so in logic, if you were basing your system on, say, predicate calculus, you'd have rules like this, that if there's something which is your dog, and this thing likes something else, then this thing will be bone. Okay, so this is some fact about the world. And so maybe you'll want to base your cognitive system on logical rules. Okay, but that hasn't worked out. Okay, so something wrong with that. Okay, so now we want to see what happens if you make this into learning. And so in robust logic, again, you've got rules, but you're going to learn them. And what the learning is going to look like is that, so the first difference is that it's equalities, approximate equalities. So if you have a black box to recognize elephants, it's an if and only if thing. The box will correctly classify elephants and correctly say non-elephants and non-elephants, and make small errors in both directions. So this implication thing is, in logic, doesn't work for machine learning. So so think of the system where, say, for every word in the dictionary, say English dictionary, you have a separate recognizer. You're going to learn a separate recognizer, say, for if the missing word is bone. So how do you recognize this? And the left-hand side will be some arbitrary complicated expression which will be learned. So the left-hand side could be a deep neural net, which takes you 3 months to train, or it could be something, could be a perceptron, could be something else. But the left-hand side is something learnable, and it learns to predict something, maybe a missing word or something else. Okay, and so maybe we for example, we could learn every English word in terms of every other word, etc., etc. Okay, but the point is that these expressions you can use for training, just like you can do logical expressions. That would be the idea, that you've got some description of the world, and you'll see whether the left-hand side of some of your expression applies, and if it does, then you kind of complete it with some more information. Okay, so you'll chain these just like you can chain those. Okay, so this is what, if you do machine learning and try to reason with the rules, this is what you seem to get. We will learn these rules. So just 1 second, 1 minute description of machine learning as I use it. So of course, in artificial intelligence, you want to acquire some knowledge and then act on it. And supervised learning is the most basic notion of acquiring knowledge and learning on it. So in supervised learning, you get examples of some flowers, which are labeled according to which species. Then someone gives you a new flower and asks you which one this looks like, and you have to classify it. Okay, so why supervised learning is so fundamental is because there the knowledge you're trying to acquire is kind of what you get access to are instances of what you're trying to do. Okay, so it's the most direct example of trying to acquire knowledge for using for some purpose. So that's supervised learning, and so there's a science of this, which is learning theory, and so the most basic promise of learning theory is that it's worth investing a lot of effort into training, because so you get a prediction error. So when you're shown a new flower, you may misclassify it, but the promise is that if everything is going well, then then your error will decrease pretty fast compared to the amount of effort you put into the training. So N includes both the number of computational steps you take and also the number of examples you use. Yes? Oh, sorry. Okay. So must be a better way. I think maybe this will work. Okay. Sorry. Okay. So our typical learning rate would be that compared to the number of effort you put in, so if you want to reduce your error by a certain factor, the question is how much more effort you have to put into the training. Okay. So anyway, so if this happens, it's worthwhile to put more and more effort into training because you're well rewarded. So, and of course that's consistent with current practice that people spend millions of dollars in training because you get rewarded for every doubling of effort you put in. So if the errors were decreasing much more slowly, then machine learning wouldn't be so rewarding. Okay, so we are, you still hear me? Yes, okay. We are going to learn these rules using machine learning. So, okay. Okay, so, because now I'm describing various features of this robust logic. Okay, so the first feature is, as I said, is that we're learning equalities. Okay. Second feature is that inside these expressions, we'll still have some sort of quantifiers. So quantifiers seem to be important in logic, and we can't quite wish them away. But quantifiers are always rather mysterious because when you say that all men are mortal, it makes a lot of sense as mathematics, but as far as empirical fact, it doesn't, because how do you know that all men are mortal? Have you searched the universe? Okay, but here everything is very clear because the quantifications are always just over this mind's eye. So if you say there exists something which is a dog, all you care about is whether in your mind's eye you have something where you're thinking of a dog. Okay, so everything you've learned, you learn about what's in your mind's eye. Okay, so you view the world through this little screen, which is your mind's eye. Everything, all the knowledge you've ever gained has come through this, and all your generalizations just are already coded up in ways which you can see through your screen. Okay, so we've got some existential and universal quantifiers, but they only apply locally. So you can check it out. There's nothing mysterious about that. It becomes clear later on. So the third question is, these are old problems in applying logic to AI, is consistency. I'm going to learn all these rules. How do I know they're consistent? Okay, and the answer is I don't, and I don't care too much. So consistency is not enforced. And the idea is that if eventually you find that you've learned rules which are contradictory, and they're important because they contradict often, then you learn your way out of it. So the classical problem people learned about in the 70s is this Nixon trapezium. So you had two rules. One was that Republicans are not pacifists, Quakers are.
shot? All right.
Thank you. Thank you. Okay. Okay. So anyway, bad time to run out of power, but okay. So in this case, you had two rules, and you had one example where you got opposite conclusions, and we're saying you have to tolerate that. But of course, if the examples where you get contrary conclusions are very frequent, then you have to learn your way out of it. So instead of saying that Republicans are non-pacifists, you'll have to say Republicans, except for Richard Nixon, are non-pacifists. Okay, so that's the idea of robustness here. Okay, so but the cost of enforcing consistency is so enormous in any other thing that this is kind of inevitable. But it's okay, we'll learn our way out of it. Okay, so just going back to learning, so we're going to use the PAC learning model, which I kind of suggested. You've got this blue circle of examples, the grand truth. Some are truly flowers of a certain species. The negative examples are truly not flowers of that species or different species. There's a grand truth, the solid line. At any moment, you've got a hypothesis, and the real world is so complicated that in any real situation you'll be making errors. They're inevitable. And so this model of learning, which we'll have to adopt for in this more logical framework. So the main idea is that errors decrease fast enough for the amount of effort you put in. It's worth putting in effort, but if you put in effort, you'll get more and more accurate. So one big mystery of learning is that it works for arbitrary distributions, but the only guarantees you get are those when the distributions are essentially the same, you learn from. And then also a general thing which applies to essentially all learning frameworks is that you're going to learn a hypothesis from a class, say a deep network class, or perceptrons, but the functions which the real world presents to you, say a teacher, you don't know what they are. Okay, so you can learn elephants, you can learn sentences about Spanish football, but you don't know what classes this comes from. And also the learning is basically a function, so you don't have to represent, you just see classifications of the truth, you don't have to represent it, you don't know how the teacher represents it, you don't know what it is. So usually it's often useful to make this rather more complex than this. Okay, so using representations which are very rich and which include instances which are hard to learn is okay as long as you're learning easier things. So that's the kind of framework in which we'll do the learning. Okay. Okay. Still doing learning. Okay, let's forget about this. Okay, so we're still doing this. Okay, so kind of the philosophically the harder part is now what's the world we're learning from? Okay, so when I say that the fact that we agree roughly on what a chair is, although we've seen different examples of chairs as children, maybe that's not so mysterious, you see it, okay. But then in this more complex questions about the world, it's harder to explain what's the distribution we're picking from. So what do what's common amongst our worlds, which makes it possible for us to understand what each of us is saying about more complex things. So this becomes a bit more surprising that it's surprising that we agree as much as we do. Okay, so to formalize this, one has to make some decisions. Some are inevitable, some maybe not. So this is one area of. But the main point still is that the examples, we don't have to describe the world. We'll just describe examples from our mind's eye. Okay, so we see the world through this screen, and all our experiences through the screen, and we'll have to find regularities in this screen. Okay, so this is what it looks like. So let's see what. Okay, so what are these examples? So let's suppose these are all Boolean features, and there are enormous numbers of them, and there's some sort of ground truth. So this is the way one sets it up, and then there's some issues. But the very important thing about this context is that this is really a world of incomplete information. So if I think about a dog and what my dog likes, I'm not describing the world very well. I've got some very partial information. Okay? And again, if you're planning on how to go home tonight, you want to go home tonight, that thought doesn't describe the world. Somehow you have to fill in your picture in your mind's eye about various possibilities, what you can do. So this area is very much about knowledge completion. Okay, so two aspects of it. Maybe one aspect is maybe this may be the So one aspect is you can have a notion of a star, which is means undefined, and here the undefined can be in the sense that it's deliberately undefined. Okay, and just as an old example, again from old AI, there's this example of Tweety, who I tell you is a bird. Tweety is a bird. Does it fly? You say yes. Then I say it's a penguin, and then you say, oh, no. Okay, and for logic this is difficult because given more information you've changed your mind. So just to point out, in a probabilistic setting you can just define this problem away, because it may be that by not defining, telling you the bird is a penguin, I'm giving you information. Okay, so it's a true statistical fact that most of the time someone says something is a bird, it does fly, because if it were a penguin you would have been told that. Okay, so the undefined often has this meaning that I would have told you if you needed to know. So some aspects of the problem of the undefined can be explained just by this probabilistic semantics without doing anything. Okay, so we're taking positions on these classical problems which did make logical approaches problematic. Okay. So it's called non-monotonicity. But that's just one example of the undefined. And the other aspect, which is somehow more important, is that we also have these question marks, which I call obscured, where there's a truth there. Maybe someone wants to tell you what the information is, but it's just hidden from you. And the question is, you want to complete it. So when you make a plan for how to go home tonight, you've got lots of question marks, and you have to complete your plan. Okay. So in general, your mind's eye will have some rules, and the rules will work on predicates which have true, false, or the star values. And when something is obscured, then you can't make predictions on it. You just don't know. You don't know whether it's going to. If you don't know whether it's going to rain, and some rule depends on you knowing whether it's going to rain, you just can't apply that rule. Okay. So at any moment in your mind's eye, you'll apply whatever rules you can, given the information you have at the moment, and you try to complete it and make a plan and explain the world. Okay. So that's kind of the setting. And then the most primitive example of this is when you've got a sentence, and the question mark means what's the missing word. That's a kind of a test case. Okay, so just the last aspect. So hierarchical learning is known to be very problematic. So if I'm learning a function f, maybe a mathematical concept, and another function g, another mathematical concept, but g is defined in terms of f, is this PAC learnable or learnable in any other sense? And the answer is that, in any theoretical approach people have taken, this offers difficulties in the sense that if the f you've only learned in some half-baked fashion, you don't understand too well, if f is still noisy in your mind, you've got no chance of learning g. Okay, so so that's why in a math class, you learn a definition, you make sure you understand it, then you learn the next one. Okay, And so the approach taken here is that's the only way. It's unfortunate, but the way this thing would be trained would be that you're given these rules and you assume that they're correct labels. You can't use as labeling your uncertain understanding of the world. Or if you do, it's problematic. Okay, so you need a teacher to tell you about many aspects of the world. Just by looking around and half understanding something, it's rather hard to build on that half understanding to learn the next concept. Okay, so no one knows how to do that. And the implication is that's probably that's hard. Okay, but if you're trained on correct labels, then you can build this thing. Okay. Okay. So this is okay. So the upshot of everything I've said is that you're going to learn these rules like this. With any supervised learning algorithm, I'll say a bit more about it in a second, and then you're going to change these rules for reasoning. As I mentioned, so we did an experiment some years ago with then student Loisos Michael, who's kind of a local here. He's in Cyprus. So the experiment was this is a very old-fashioned NLP and machine learning by present-day standards. We used the Wall Street Journal data set, which was standard at the time. We used parsers, whatever was available. We weren't too purist, so any resource which we knew was highly reliable, like WordNet is an online dictionary, we were willing to use it. We didn't want to just show that we can learn everything, okay? But the difficulty in all these things is that mixing up unreliable things with reliable things is dangerous, okay? Because once you train, unreliable things compound. So we did various reasonable things. We tried to learn rules about the world from single sentences in this Wall Street Journal. So you think that one wanted to learn facts about business or economics or something like that. So that's what the Wall Street Journal discusses. In fact, it's not clear how much you can learn from the Wall Street Journal. It's mostly kind of gossip about who is being fired and that kind of stuff. And then, so the question was, how much better can you do by training these rules we've learned to predict the missing word? We're still in the same problem compared to a baseline syntactic method. So the problem is, in this game, is that this black box machine learning is pretty powerful, okay, because it uses a lot of examples of what it knows about, so it's hard to compete with. So what you do, you have to somehow do as well as that. You have to compare yourself with the best machine learning box you have. And so this, so what I'm describing here is an experiment which should be done 1,000 times better now, but needs to be done. Okay, so then, so this is a typical rule which the machine managed to learn. So, so this is price Y. So this was going to predict whether your missing word is price. Okay, price occurred quite often in these Wall Street Journal sentences. When is the missing word price? And then the learning method we used was a perceptron-like. It was Littlestone's winnow. So it was a linear inequality. So there's various things. Question was, did the evidence add up to at least one? And the evidence was something like, was another word X, which lowered this missing word Y, and if the X was bargain. So if the Wall Street Journal said that this bargain lowered blank, then you said, it must be price, okay? And then there was various other evidences, piece of evidence for when it was price, and this rule somehow could manage to add it up. Okay, so this seems to pick up some knowledge about the world, which isn't just kind of about the syntax of sentences. Okay, and of course the question is, if you learn this stuff, can you do better on a basic NLP task than you could with that? Okay, so that's the game. Okay, you have your one box for doing your task, your one black box for doing your natural language task, and now you're saying, well, can I do better if I train 1,000 different boxes? which do some reasoning, and okay. And the problem is that if you go through 1,000 different boxes and do some reasoning, you introduce some more errors and uncertainties, and that's the trade-off. Okay, so and of course the single black box may pick up a lot of information, but I don't think it picks up everything. So in this experiment, there's a small data set, this Wall Street Journal. Okay, so we picked the target words which occurred most frequently. Price was among them, and we saw how well we did, and then with some. Okay, so roughly what these, what you should look at here is that our 268 words we arranged from left to right, and the rightmost ones are the ones where our method did best, and then our method was E, and if you just use a single black box, you got D. So between the E and the D line on the right-hand side, where there's a big gap, it means that for some words we did really well by understanding a bit about the world. But on the left, noise kind of spoiled everything. So this was a telltale sign that you could compensate for the errors induced by any kind of chaining by doing this. Okay, so as I said, this experiment should be done 1,000 times better. So how much more time should I have? Sorry? 10 to 15. Okay, sure. Okay, so I've got two slides of slightly more theoretical background. So repeating myself a little bit. So this is the setup. I've got T objects. These are the tokens in your mind, and maybe T is 20. So the right-hand side of the rules, I said, were things like bone. In fact, you could have relations, binary relations, where you're learning to recognize a relation on two objects in a scene. Something, what was next to mean. I'm learning what next to means of two people. So the left-hand side of the rules is your favorite learning representation. So you could have linear inequalities. If you use perceptrons, you could have deep learning, if you like. And so the important thing is that all these learning methods are propositional. So the methods work on Boolean bits. I suppose every learning method works on Boolean bits. If you, like a vision thing, works on pixels. But here, so we have these relations. We can make compound features as given the resources we have. Of course, the number of compound features blows up as exponentially if you do it too clumsily. But you can have a feature which says one relation and another relation, and these x1, x2, and x3, x4 are different objects in your mind's eye, and there's some quantification. So is there an object x1 in your mind's eye, which is a dog and something else, and such that everything else in your mind's eye, etc. Okay, so we can have compound things like that. Okay, and the idea is that all these things are the right-hand sides of some rule, so you know how to recognize that because you've learned it. Okay, and then you have a propositional learning algorithm which does what you want, and what learning algorithm you use, whether it's deep learning or perceptrons or whatever, you can choose depending on what characteristics you want. So you may want, so attribute efficiency is when there are lots of irrelevant attributes, and if the small ones are relevant, and some algorithms are very good at being efficient and not being distracted by lots of irrelevant attributes. You can also choose deep learning, but that's very computationally expensive, so it's not the obvious choice. So if you're going to learn 10,000 different functions, the cost is 10,000 times the usual deep learning cost. Okay, so we have to do different. If you do an experiment, it's not clear how to choose the learning method. And then, okay, so there are some. So what's promised by the system? Okay, so the rules are learnable. That's kind of by definition. and you want the training of the rules to be polynomial time. But the main promise is the soundness. Okay, so essentially what the promise is that if you learn these rules, they're learned in the PAC sense, in that there's a promise that this may be 99% accurate. Okay, you've got lots of rules, 99% accurate. So now you're going to chain them together. So you're going to chain two together. So what promise do you expect? Maybe 98%. Okay, so that's basically what's delivered, that even when you chain together, you've got some bound on the error. Okay, so for each rule, the bound on the error is kind of promised, and this promised makes sense by how much data you've given it. But now we're going to chain them together. You need some other guarantee, and the guarantee is some little theorem which says that the chance that in that space both rules are wrong, or either rule is wrong. Okay. So that's the main thing. There's also some sort of completeness. Okay, sorry, I'm saying the same things. So to make this, okay, so of course the issue here is that we're doing some learning, we're doing some reasoning. Also we are in this multi-object world where you've got these x's, different x's lying around. And we want to keep everything polynomial in the worst case. So we're fighting on three fronts. And it turns out that the only restriction which you have to put in, which ensures polynomial time for everything, is that your relations need to keep constant arity. Okay, so as long as I shouldn't have a relation on 100 people. So question of whether an odd number of people in the room, that would be a bad relation or a prime number of people in the room. But relations saying that people at the front and people at the back, classifying the world into smaller. So I always have to think of a small number of objects in the world and relations on them. Okay. So in my mind's eye, I can the dependence of complexity is just polynomial on the mind's eye. Okay. So this emphasis that we can only have 7 plus or minus 2 concepts in our heads, it's not that bad. But each relation which we can handle, we have to decompose the world into relations with constant arity, because things will be exponential in the arity of the worst relation. Okay. So otherwise, we can have the number of rules we have, how big the rules are, number of objects in the scene. We can deal with that. Everything will be polynomial in that. Okay. So the constant arity condition isn't one which people objected to. Okay. Okay. So if I've got this theory, what's wrong? Why don't I just solve the AI problem? Well, one big problem is data. Okay. So one thing we've learned from the deep learning people, of course, is that having good data sets is crucial. Okay. So a big part of the deep learning history is the importance of important data sets. So where should we get data to train our machine to be intelligent and learn all these rules? What about the web? Okay. Well, unfortunately, that doesn't quite work. So supposing you want to find out from the web whether what color an elephant is. Okay, recent work. So this is what we get as far as the number of hits. Okay, so that wasn't very useful at all. So then the next thought is, well, let's do science. Let's go to Google Scholar. That should give us the answer. And then we get this. Okay. So the idea that we can get useful teaching materials from just anywhere is wrong. In the data used to show the efficacy of, say, deep learning, people had very, very carefully constructed data sets. And so how to train a machine to learn common sense knowledge is a really hard problem. How to prepare data. Okay. Okay. So these are okay. Let's forget about that. Okay, so as far as the teaching material, so the point I've been making for quite a while is that making proposals for the algorithmic part of this project, having learning algorithms and having some reasoning algorithms. So that's doable. I've given you some examples, and what the alternatives are may be clear. But the hard part always is the preparation of teaching materials. It may be an endless task for humans to prepare teaching materials for machines, which reflect the enormous amount of effort humans take into educating the young. Okay, so we've got education institutions like this one. A big part of the effort of the education institutions is to prepare teaching materials, updating them. It's an enormous effort. And I suspect that to make machines intelligent in this sense, it'll be the same thing. So if you want to spread the value of AI, most of what you'll be doing is to figure out how to put relevant knowledge into machines using methods which are kind of out there. So you don't have to invent new methods, algorithmic methods, but preparing data is difficult. Okay, so the main challenge is some big experiment, better than one I showed about the Wall Street Journal. So I'd be interested in any ideas anyone has in the audience. So it would be interesting, for example, to exercise this in some domain which is still restricted. So you need some domain where there's a lot of data, but there's evidence that you have to do there's some real world, some rules about the world which are worth discovering. Okay, so when you train a network to recognize elephants, we don't think that the difficulty is that we have to discover some new rules about how elephants are constructed. We don't think that. There are lots of examples of elephants in different positions, and you just have to learn that. But in some areas, it may be chemistry. I'm not quite sure what a good area is, where there's a lot of data, and there are a lot of rules which haven't been enunciated by humans, and the machine can discover. So that's the kind of area where it may be possible to illustrate this. So something like the Wall Street Journal it may not be the perfect context. Okay. Okay, so in informal terms, okay, so this is the practical aim. You want to be able to put into machines general knowledge in such a way that you can robustly reason on it. That's the practical challenge. And the main claims are that the three main claims are that the learning enables you to keep the system consistent and provides robustness. So whereas this project of making systems reason with common sense knowledge, that didn't work out. For using logic, the hope is that it does work out if you use learning. Certainly if you want to put in knowledge which is nowhere defined, it's only defined by example, then you certainly have to do just learning. And then the remaining problem is principled reasoning. And so this is, okay, no, let's forget about that. Okay, principled reasoning. Okay, so I think we'll go to thank you. Okay, thank you. Yes. So the question of if I only wanted to determine factual questions, then there are methods of determining that from the web. If you wanted to find out the birthday of a U.S. president, there are ways of doing that, and there are systems for doing that. Okay, so I think the unsolved problem is when you try to find learning data for common sense reasoning. Okay, so for factual knowledge, people successfully do that. You're right. So I wasn't trying to suggest that was an unsolved problem.
Maybe may I ask a question? It's 4 decades since you introduced computational learning theory. So how do you feel about this area conquering the world?
Oh. Well, okay, no complaints. You know. Okay,